Okay, this is the 4-3 notes for Calculus 1. In section 4.1, we talked about how basically identifying absolute and local extrema, but we stuck to just the calculus methods for determining absolute extrema, and I mentioned we'd be returning the local extrema later. Well, that is what this section is all basically going to be about. So we're also going to be returning defining critical points as well, because that's a key part of the process. But we start with the definition of an increasing and decreasing function. So the definition's a little involved, but just if I was to just summarize it in the best way possible, basically a function is defined as increasing if you take an x-coordinate and you find your y value at that x-coordinate by plugging in a function. Then you take your second x-coordinate and find its y-coordinate. And of course, if this is larger than this, then the function must be increasing. Okay, it's very super simple. Same thing goes with over here. If you find your first point and it's up here at f of x1, right? And then you find your next point, which is down here at f of x2, then if you're going from here to here and the y's are decreasing, then of course we're going to have a decreasing function. So this is exactly what this definition is stating right here, but just in with a graphical explanation, which is much easier to come up with. But even though this is true, this doesn't necessarily, that's more of an algebraic interpretation. We need something where the calculus comes into this whole situation. So let's say we did that. So let's get rid of some of the stuff, sort of the stuff that we put in here. And let's say that I wanted to use tangent lines to break this apart to understand. So just look at this increasing function here. So let's say if I put a point here, and I drew a tangent line, and then I put a point here and drew a tangent line, and then I put a point here and drew a tangent line, something like that. What appears to be happening with all these tangent lines? What type of number would we represent as the slope of all these tangent lines? Well, it appears that they're all rising lines, so we would consider them to be positive slopes. So therefore, slopes of tangent lines on every point of an increasing function are positive. Okay, that's a big deal. That's going to help us really determine whether a function is increasing in different parts of its interval when we don't have the graph, because when do we ever have the graph, right? So if you look here at this function, so I draw a tangent line here, I draw a tangent line here, draw a tangent line here, let's say. What do we know about this? All of those slopes, they're all falling from left to right, so they're all negative. So anytime you have a decreasing function, the slopes of the tangent lines at every point will be negative. Okay, so that is the key concept right off the bat, is that we can determine if functions are increasing or decreasing based on an interval, based on the slopes of their tangent lines. Okay, just to summarize our theorem here, suppose f is continuous on some interval and differentiable at every interior point of that interval. So again, just like we have seen before, continuous and differentiable in concept. Then if the derivative is greater than 0, in other words, positive at all interior points, then n is increasing. If the derivative is negative at all interior points, then f is decreasing. Just that is the theorem that for the test of any intervals. And note, this is not for the entire graph, because I mean, if we have polynomials can be like this all over the place, right? They can be, that's really bad. Oh boy. That can be, polynomials can go everywhere. So in some intervals, it's going to be increasing, and then some it'll be decrease, and so forth. So it's not on the whole graph, it's just on a specific interval that you set aside. So just remember that the derivative on that interval will tell us whether it's increasing or decreasing. Okay, so back in section 4.1, a couple sections ago, we used critical points in order to identify where the absolute min and maxes were. That was a very straightforward process most of you probably did fine with. Now what we're going to do, and the whole point of this section, is that we're going to again use critical points to identify local extrema, but there's a catch. We're going to have to analyze the positive and negativity of the points surrounding the critical points. Okay, so this in the beginning is a learning curve on understanding what it's about. So instead of just jumping in the problems, I do a little bit of explanation here just to make sure that all is good with understanding what's going on. So this is called the first derivative test. The first derivative test is how we identify local extrema within an interval on a graph. So what I want you to do real quick is I just want you to look at our first graph over here on the left. Let me change to a different color. So what we have is basically an upside down parabola for our function here. So upside down parabola. So basically what we do is we identify a critical point. And if you look at this graph clearly, there's going to be a critical point right here because this is going to be an extreme value, right? So for sure there'll be a critical point there. We already know that's the case. Why? Because anywhere where we're going to have a horizontal tangent line with a slope of 0, the derivative is going to be 0, and therefore we're going to identify a critical point. That should have been sort of something that you have in your brain already. So what we do is instead of analyzing just the point, we analyze the surrounding values. So for example, let's say that we took all the points leading up to, in this scenario, leading up to that critical point. What do we know about all the slopes of the tangent lines leading up to that point? It looks like they're all positive. In other words, derivative is greater than 0, right? So what if we went on the other side? What if we went on this side, on the other side of the critical points? So what do we know about all tangent lines on this side? Well, it appears that they are negative, or in other words, the derivative is less than 0. So the key is understanding, if we know that all the slopes of tangent lines on this side leading up to the critical point are positive, and all slopes of tangent lines coming from the critical point are negative, that means that we must be creating a top tangent line that's horizontal. That's the only way that's going to work. If you're going to go from positive tangent lines to negative tangent lines in terms of their slope, then somewhere at the top it's got to come to a horizontal, which, what does that do? That creates a maximum point if it's positive to negative. Therefore, our first part of our definition states this. If the derivative of a function changes from positive to negative as x increases through c, then we have a local maximum at that critical point c. Okay, that is the first important concept of this section, is understanding that if we go positive to negative, it creates a local maximum. Most students will just write it. So they'll be like, okay, so we go from positive to negative. What does that create? That creates a local maximum. You can see it just by drawing it out, right? So what about the next one? So look at our graph over here. So what if we have our critical point identified right here, which of course creates a horizontal tangent line? What if we have all points leading up to it, if drawing tangent lines to those points would create a negative slope, so a negative derivative. And then from that, if we leave the point on the right side of it, all of the tangent lines have a positive slope identified with it. So if we go from negative to positive, we create again, a horizontal tangent line somewhere in the middle, but more importantly, we create a low value or a local minimum. So again, take the derivative. If it goes from negative to positive as we increase through the graph, then we have a local maximum at the point C, our critical point. Okay. This is how we identify local and mins and maxes. Now, there's going to be a whole procedure for this, which is something you're going to have to learn and memorize how to do. But for now, this is the concept that we're getting at when it comes to identifying local and extrema. Last part, though, there's a key element here that we have to make sure that is all set. So this right here, it's very important. So if we go down to another graph, look at this. So what if we identify a critical point right here? And we identify all the slope of the tangents leading up to that point as positive. But then we identify the slope of the tangents leading after that point, going away, as also positive. Well, look at this graph for a second. Does this appear to be a maximum or a minimum on this graph? Hopefully when you see it, you say no, because there's just nothing happening there. It's just a point that it goes through that is not max or min. So whenever you have slopes coming and going that are both positive, that means there's going to be no local max and min at those points. So here, this is an interesting development, because note that this was a critical point either way. So it turns out that when you have a critical point, that doesn't necessarily mean that there's going to be an extrema at that point. So be very careful with making that judgment. So when you move on to the next graph, it's the same idea. Let's say we analyze the slopes before and after. They both are negative in this scenario, right? They're both negative. So if I have a critical point and I have a negative before and after, that's also going to create a situation where I have no max or min. So it's not about the sign, it's about the fact that they have the same slope before and after, whereas these have opposite slopes before and after. So if they have opposite slopes, they create a local max or min. But if they have the same slope, they don't create anything when it comes to that. And that's what this says here. It says if f prime does not change sign, positive, negative, or negative to positive, then f has no local extreme value at that point. That is the first derivative test in a nutshell. As long as you get that, then when we do the problems, the example problems, you're going to see why this all sort of comes together very nicely. Okay, so before we get started with number one here, just realize that basically this concept that we're about to do, which has multiple parts in this section, is a gigantic part of the curriculum. So again, you're not going to get this graph right here, right? The graph of this function. So you're going to be asked to identify a bunch of characteristics about a graph that you don't see. And the whole point of it is to go through the process that I show you in order to identify them, okay? You have to know this process inside and out. If you don't, this is going to be on all labs, it's going to be on all homework, it's going to be there's going to be big points on the exam related to it, so you must be able to do this without a problem. Too much on the line in terms of your grade not to. So, what is the process involved with this? So, the first step in any identify local extrema type problem is to find the critical points. That is what we need in this problem. We need to know the critical points. So it's the same first step in your absolute extrema problems. How do you do that? You find the derivative. And then you'll set it equal to 0. So real quick, we're going to get 12x cubed minus 12x squared minus 12x plus 12. Okay, people seem to like 12s here. So if you're looking at this, that should be for really quick derivative defined. Then, of course, We're going to set this equal to 0. Okay, but note that we do have a GCF of 12. So we can take that out, and we can get this as the equation that we need to solve. Now, as I've been doing in previous sections, I've been slowly bringing back algebra concepts that you're going to need to know. And here's another one. So this is a factoring a third-degree polynomial that has 4 terms. Okay, if you recall, the method for that is called grouping, factoring by grouping. So we need to make sure we review that so there aren't any issues. So this 12 is going to sort of stay put on the outside. So let's go through the process that you do that with. So when you factor by grouping, you basically mentally break these up into each 2 pieces, and you find their GCF. So the GCF of the first 2 is x squared, so we get x minus 1. There doesn't seem to be a GCF of the second 2, but our goal in a grouping problem is to match this with whatever we get on the other side. So this should be x minus 1. Again, well, how do we get x minus 1 out of this second part here? We have to take out a negative 1. So we get this as our next part. So again, the 12 comes over. So how do we do the rest of the factoring? Well, right now we actually have another GCF. This is sometimes hard for students to conceptualize, but if you look at this right now, don't we have 2 of the same values twice in an equation? You do. So we can actually factor out the x minus 1, and we're left with x squared. So let me do this instead, different color here. X squared minus 1 left over right here. Whoop. X squared minus 1 equals 0. So that is called factoring by grouping. If for some reason that lit your world on fire right there, then obviously go into Google and just type in factor by grouping, and you'll do a couple examples, and you'll all be caught up. Okay, so moving on. So we have 12. We can get rid of the square brackets. X minus 1. We also have a difference of squares, which we can factor into x plus 1 times x minus 1. So this is the same as that. And then finally, we can say that this is x minus 1 squared, x plus 1 equals 0. Okay. So we didn't have to do that step, by the way, but because the key is we need to set all the quantities equal to 0. So basically, if you want, you can just ignore this. It's up to you. It doesn't really matter. But you have to set all quantities equal to 0. There's 2 x minus 1s. We don't have to do it twice. So we're going to get x is equal to positive and negative 1. Okay, so what does that mean? That means that these will be our critical values or critical points. It doesn't matter how you write it. If you want to say CVs, CPs, I've seen it done both ways. I know in previous sections I've been calling them critical values. It doesn't really matter. So what does that mean? So that means that in our graph, our potential local extrema are at x values of positive and negative 1. Okay, so let's pause for a second. So if you recall in section 4.1, when we did absolute extrema, we also identified possible values, but those possible values didn't only include critical points, they also included the endpoints, right? Whatever, endpoints. So we had multiple values in which we did x, y charts for. That does not work in this scenario. Why? If you recall, we cannot use endpoints when it comes to identifying local extrema. It's only interior points. And in this scenario, they don't even give you endpoints. They're asking you on the full spectrum of the graph, what will be our extrema, our local extrema. So it's a different setup and a different scenario. We do start the same. We find the critical points, but the endpoints are out of the picture, and all we care about is that we could have local extrema at positive or negative 1. Okay, small side note just as an aside here. So remember that critical values or critical points occur not only when the derivative is equal to 0, but also where the derivative does not exist. It's an important designation that you remember. So if you look at this particular problem, we have a polynomial. You do not have to worry about where the derivatives fail to exist at a polynomial because that does not happen. There are other scenarios where it does happen, which we will touch upon soon, hopefully. But just generally, when it comes to this, you want to keep that in the back of your head. You don't want to lose track of that. So just because, in this problem, we solved for when the derivative was equal to 0, we didn't have to do where the derivative does not exist. Okay, so this is where things change a complete sort of, it goes in a different direction. So the procedure for tracking down and identifying local extrema, as well as whether a function is increasing or decreasing, is all about using what looks like a number line. So you'll see what I did here is I drew this blue number line from horizontal left to right with arrows. So what you do with this number line is you always plot your critical points. They always go, you put them in the right order where they go. You don't need any other points but those on the number line, -1 and 1. So right, these guys, right? So from there, what you're going to do is you're going to use this in order to identify when this actual figure is increasing or decreasing so that we can determine local extrema. So if you look at this is what you do. So first things first, you need to do this. So you need to evaluate a value to the left of -1 in the derivative. So I usually just take the next integer. So we want to evaluate -2 at our derivative. We also want to go between -1 and 1 and identify a value, hopefully an integer. Sometimes it can't be, but usually it is. So we're going to identify 0 for that derivative, and then to the right of 1, we'll take the next integer, which is 2. Okay, note, does it matter which number you pick in that interval? No. All of the behavior to the left of -1 is going to be the same. What do I mean by behavior? It's either going to be increasing or decreasing, and that's it. Because we know that the slope of the tangent line is 0 at these 2 points, right? Isn't that what we solve right here? So that means before it, if there's no critical point anywhere over here anywhere, that means it must keep on going either positive or negative. Same thing in here. If there's no critical point in between -1 and 1, it must be either positive or negative, increasing or decreasing between them, and that only. So I could have picked a half. That goes in there. That would have worked. But why do that when evaluating is much easier? Same thing on the right. So if you take derivative of 2 with derivative with 2 evaluated, I could take 3, 4, 5, 20, 70, anything on that side, they'll all be the same sign. Okay, so the key is, though, you want to make sure that you are plugging these into the derivative. So in the previous section, what did we do? Or the 4-1 section, we plugged and substituted it into the original equation because we wanted the heights. We don't want to do that. We want to sub these values into the derivative because it's going to give us the slopes of the tangent lines and whether they are positive or negative. Isn't that what we want? Remember, what are we trying to evaluate? We're trying to find the slopes of the tangent lines to the left and the right of our critical points. So we need that in order to do this. Okay, so let's go ahead and do that. So it is wise for you to use your fully factored equation in order to accomplish this step. So right here, this equation right here. So this is extremely useful, and I'll show you why. So let's say that we substituted -2 into here. we would have to use the calculator. I mean, plain and simple. I mean, you're not going to do it. There's no way around it. You're going to have to plug that into the calculator. But if you use this, look what happens. So if you plug -2 into this x right here, you're going to get a negative number. If you plug in -2 into this right here, you get a negative number. If you plug -2 into this, you're going to get a negative number. And of course, 12 is a positive number. So what do you get when you multiply a positive times a negative times a negative? You get a negative number, which is what you put right there, right in that space under f prime of -2. Just to reiterate, if we plugged in -3, -5, -9, -100, all of those numbers would create the same pattern of signs that would basically allow us to say that this is going to be a negative number that will be here. That is the key on every step that you do this. You just plug it in and find that. So let's say you plugged in now 0, so this right here. So if we plug 0 into this, we're going to get a positive for 12. 0 minus a -1 is negative. 0 minus 1 is also negative, but 0 plus 1 is positive. So if we do a positive times a negative times a positive, what do we get? We get a positive. So now every value between -1 and 1 is going to be positive in terms of the slope for our problem. Last one, if we plug 2 in, we're going to get it. The 12 is positive. We plug 2 in, we get 2 minus 1 positive, 2 minus 1 positive, 2 plus 1 positive. So what type of number do we get? We get, again, a positive number for what we're doing here. Okay, so let's make some judgments here. So let me do sort of a summary. So right now, we can determine when our function is increasing. So this function, we'll just start with decreasing. This function is decreasing on what interval notation set of values? Well, anywhere where there's a negative sign. So it's anywhere from -infinity, which is always a parenthesis, -infinity. And then where are we going to where it's no longer -1? We're going, or no longer a negative slope, -1. Now it's very important that you put a parenthesis here, because remember the slope at -1 is 0. So make sure that it's a parenthesis only. So this function is decreasing from -infinity to -1. Now, I think it's very important that we stop for a second and look at our graph. So ignore the blue line, dashed line, look at the red line on our graph, this guy. So we identified our critical points as -1 and 1. So far, -1, we're basically at this point right here. So look what we just found. We just determined that this function is decreasing from -infinity to -1. Hey, look at that. We're right. So this is what you actually just did, believe it or not. And it can be overwhelming in the beginning, but that's what you just determine by finding these slopes. So what else do we know? Well, look at the rest of the signs on the graph. They're all positive. So that means we know that this function is increasing on, it looks like from -1 to 1, -1 to 1, and then from 1 to infinity, with a union between it. Now, a small thing, I sort of like this way as a way to write this, but I found in my math lab that they're a little bit different with this. So they consider 0 to be, part of the positive numbers in terms of what it is. So in my math lab, they might write -1 to infinity as the spectrum in which this is positive. So I don't love that. I wasn't even taught that to begin with when I was in school, but I tend to be very anal about just doing the union symbol, but just realize they could say -1 all the way to infinity, because this basically is 0. It never changes positivity. Okay, so note, we have identified some of the answer. We have identified where this is increasing and decreasing. So that's the first step, so to speak. The second step is not a whole lot of work. It's just analyzing our graph again to determine where the local extrema are. Okay, that's the key. So this is where our first derivative test comes in, right? So this is what I tell students to do. So at -1, it appears that the sign is changing from negative to positive. Anytime the sign changes, that means we have a local extreme point. But we have to determine what type of local extreme point, maximum or minimum. So if we go from negative to positive, then that is this one right here, this guy, which means we have a local minimum. But do we really have to always go back and memorize that? Not really, and I'll show you why. What I tell students is to make a little mini drawing right here. So if you're going from negative slopes decreasing to positive slopes increasing, what type of local extreme value do you get if it's at the bottom? It's a local min, right? So then we would write that there's a local min at x is equal to -1. And again, in your labs, if they ask for the coordinate, you have to be careful here. So obviously it's going to be -1, but then when you take -1, you need to plug it into the original function, right? Because we need the coordinate that was on f of x. So make sure you realize that. So that's going to be, if you do that, it's going to be -10, which is, I'll put a note here. This is f of -1, okay, when you get it. So that is local min at x equals -1, which is the coordinate -1, -10, which is right here, by the way, right? So if you look at the next critical point, analyzing this one right here, do we have a sign change or no sign change? Well, it's double positive, so we don't have a sign change. So which one does this actually look like? It looks like this one right here. So even though you don't really need to draw it, but it literally looks like this. And because it's not a sign change, that means that there is no local extreme value that is occurring there, which means you don't have to write anything else. Which means the answer to the problem, believe it or not, is this entire summary right here. It identifies identifies increasing and decreasing, and it identifies all local extreme values. Okay, so let's return to the graph once again. So do you remember here we identified between -1 and 1 we are increasing? Let's verify that. So between -1 and 1, it appears that we are increasing. In other words, all the slopes of tangent lines are positive and the function is increasing. Then what do? We go to 1 to infinity, and we go, all right, well, that's here. And that goes all the way this way, right? So what do we know about the function there? It is positive. So we recreated the entire graph's behavior without the graph. The graph is great for checking, but that's what we did. And if you look at the graph here, look at that point. Is that a local min or max? I sure hope not. That is just an in-between value, which we were correct in identifying that wasn't an actual local extreme value, unlike here, where we were correct in identifying that was a local min. So you can clearly see that there's a lot going on here. The graph basically shows you in the end that the reason why you did everything and everything you got, but note you're not going to have the graph. The one thing I wanted to point out, though, just so that everybody sees is, you see this blue line right here, this blue dashed line? That dashed line is the derivative. So believe it or not, if you look at the derivative, basically, if you solve the derivative for 0, you're going to get wherever the derivative crosses the x-axis, right? And it turns out that the derivative crosses the x-axis wherever this graph has critical points. It's actually a really neat concept, but that's why this whole problem works, and this concept works with critical points, is that we will always identify that, be able to identify them by where the derivative is 0. So I'm not going to lie, that this problem can be a lot to take in when you first learn it. So I can see why some might be a little bit overwhelmed. They're just like, wow, like that was a lot. It's again, just like all math, it's about practice. You can't get away with not practicing this stuff. So if you continue to do problems and homework and labs, eventually it's just going to become second nature to you in order to do so. So why don't we move on, do another problem, and just keep on getting practice, because that's the best thing to do in this standpoint. So let's take our attention to number 2, where we're dealing with now a rational function, x squared over x minus 2. Again, what is our directions? We have to determine whether it's increasing and decreasing, and we have to identify any local extrema. Same process, basically, right? So that's where we're going with it. So let's, right in the beginning, same process, we need to find the derivative of the function because we need to identify critical points. So the derivative, we need the quotient rule. Yes, we do. So make sure that you are all ready with this. This is exactly why I said earlier, memorize these rules. Don't rely on going back every time. It's just going to take too much time, and you'll be way ahead in calculus too, in terms of understanding everything. All right, so we do our little quotient rule, our usual. We're going to get 2x times x minus 2 minus x squared times 1 for the derivative over x minus 2 squared, which is going to give us distributive 2x squared minus 4x minus x squared over x minus 2 squared, which will finally give us x squared minus 4x over x minus 2 squared. Okay, so this is the derivative of our function. So what do we always have to do? We have to set that derivative equal to 0 and solve. So x squared minus 4x over x minus 2 squared is equal to 0. Hold on, extra parenthesis. Is equal to 0. Okay, so we've done a problem like this before in the absolute extrema procedures. What would we do next? We would multiply both sides by x minus 2 squared. But what does that do? That eventually basically eliminates the entire denominator. So all we care about is x squared minus 4x equals 0 and solving that. This is a binomial. We also talked about review with this. This is all about GCF. X times x minus 4. If you set both equal to 0, we're going to get x is equal to 4 and 0. So these guys here are going to be our critical values. Okay, now I have to hit a pause button here because if you recall, I was very keen to point out that we have to be careful that we don't just look at when the derivative is 0. We really have to look at our function to see if there's any other places where the derivative could not exist. So real quick, look at our function. Is there anywhere where the derivative does not exist in this function? Well, we know it's a rational function, so there's no corners or cusps or vertical tangents, but we do know that most rational functions do break continuity. So where does it break continuity in this problem? That should be really easy to see because division by 0 is a problem. So that means in this problem, we also have x equals 2 as a CV because f of x is not differentiable there. Okay, so we have 3. Now, I do know, obviously, some students are going to miss that, right? So I would just be very careful when you look at your original equation that you see that, because that now has to go on your number line. So draw it out. So 0, 2, and 4. Okay, so move this out a little bit. All right. So doing our number line scenario for this, we have to accomplish this the same way. We need to find integers in and around these values. It doesn't have to be an integer, just to be clear, but it would be nice if it was. In around these values that actually can be plugged into the derivative. So for example, to the left of 0, we can plug -1 into the derivative. Here, we can plug 1 in. Here, it looks like 3 falls between 2 and 4. Here, let's just pick 5. Could have picked 6, 8, 20, doesn't matter on the right side. Any number in the interval. So what are we doing? We're taking these values and we're subbing them into the most factored form possible of the derivative. So what I did here, so this actually can be factored a little bit more. That can actually help us out. So we can actually take out an x times x minus 4 over x minus 2 squared. And that'll help us even more with our math. So I want to point something out here. Look at the denominator of this thing. No matter what number I plug into that denominator, what type of number am I getting? Well, if you look at the square symbol, you know that it'll be positive no matter what. So this is going to be a little different because here, when I plugged in the numbers here, it was like something times something times something. Now it's going to be something times something over something. And that's no different. It's the same concept in terms of this. So let's try, I'm going to do a couple of them out. So what do we need to do? We need to plug -1 into this. So -1 into x gives you a negative. -1 into x minus 4 gives you another negative. And then that's divided by always a positive. So what is a negative times a negative divided by a positive? It is a positive. Alright, so what about 1? If we plug 1 into this x, we get a positive. If we plug 1 into this x minus 4, we get a negative. And the bottom is always positive no matter what. What's a positive times a negative divided by a positive? It's a negative. Okay, so hopefully by this point, this is becoming very quickly understood when it comes to the negative signs and the multiplication. That's all we're doing the whole thing. So again, what if we plugged in 3? We would get a positive, we would get a negative, and we would get a positive. So that's going to be a negative. What if we plugged in 5? We would get a positive again. This one would become a positive. This would be a positive. Therefore, this is a positive. So this is our number line that we actually created. And all of the results from our problem now come from this number line. So this is gold. So the problem is students who don't get this will, if they don't get the number line, then all the answers are going to be wrong. So you have to be very careful when you're developing this that you understand the process. So here we go. So where is this function decreasing? So this is decreasing on wherever we see negative signs. So we're negative from 0 to 2 and from 2 to 4. Note, again, always parentheses, because what do we know about the value of the slope at each one of these values? It is 0. That was the whole purpose, or does not exist, by the way. So this one's undefined, but it's 0 or does not exist, so that's not going to help us. So basically it's decreasing on 0, 2 to 2, 4. Now, just a note here. So this is why I hate that my math lab does this. What did I show? Oh, this right here. Remember this? Instead of this right here. This is why I hate that, because in this example, you can't do that. Because there's a big, gigantic asymptote here, which means that can't be included in your negative interval. So that's why I'm not a big fan of the way they do that, but it has to be the way I wrote it there. Okay, when is this increasing? Well, it's increasing on wherever it is positive. Well, it's positive over here, which is from negative infinity to 0. And union, we start at 4 on the right side and go to positive infinity. Okay, so that's the first part of the problem. The first part is identifying where it's increasing and decreasing, which is what I highlighted in purple right here, right? So now we have to identify local extrema. So this is where we have to do a little analyzing. So in green, what I'm going to do is I'm going to look at where this, well, first of all, I'm going to look at where there's a sign change. So there's a sign change here, not here, and yes here. The key is seeing that. So we now know that there is no local extreme value here. That is out. Why? Because it goes negative, negative. So we know, by the way, that it's going to look like this. But that's not of importance to what we're doing. That is just identifying that we don't have to know what that is. So in this problem, there are going to be two local extreme values at 0 and at 4. So the question is what type of extreme values are there? So this one goes from positive to negative. So just watch. I'm just going to do a mini picture, and it'll just fly off the picture, off the screen from you. So if I go up, 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 increasing, down, 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 decreasing, what type of extreme values at the top? It is a local max. So there's a local max at x equals 0. And if you want to plug in that number, you will get a coordinate. So worth noting that if you plug that number into the original function, which is here, you're going to get 0 as your value, because you're going to get 0 over negative 2, which is 0. Next, we go over to the other possible value of an extreme. It goes from down, 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 negative to up, 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 positive. So that creates a local min value. So local min at x is equal to 4. If you plug 4 into our original function, not the derivative, then we're going to get, looks like 0, 4, comma 8 as our value. So this is essentially the answer to your problem. You'll have to be able to come up with that in terms of what the calculus works out to be. Okay, so the analyzing of increasing and decreasing functions and identifying local extrema is only the first half of the process, believe it or not. Okay, so the ultimate goal is to be able to hash out a graph and determine what it looks like from scratch without actually having plotting points or having a graphing calculator. So the idea is, if you recall a while back when we first did higher order derivatives, I mentioned that the second derivative is actually going to come into play at some point as being important, and now that's exactly where we are. The second derivative is going to be very useful for us with what we're about to do. So let's take a look at this function, x cubed, which is graphed over on the right over here. So the function itself, which basically I'm going to trace through here since it's a little bit hard to see. So the function itself is like that, right? It's just the graph of x cubed. Let's just take a peek at what's going on with the tangent line. So you can see all the fuchsia pinkish type color there. So those are just tangent lines that were drawn to the graph. So if you look at the right side, so anywhere from 0 to the right, if you look at what's going on, you'll see if you draw those tangent lines, interestingly enough, the tangent lines all appear below the graph. Not all students see it right away, but look, everyone I try to draw, they're all below the graph, like physically below the graph. Whenever that happens, we refer to the graph, that portion of the graph, as concave up. Concave up, right? Another way to remember it is that the graph basically opens up. So when you look at a graph like this, it seems to be opening up where the piece right there is sort of cupped in the up direction. So that is concave up. Now look at everything to the left side of 0. Now look at this graph right now. Look at all the tangent lines. when you draw these tangent lines, where are they physically in relation to the green curve? They're actually above it this time, whereas these were below it. Now these are above the line. Whenever you have all the tangent lines above it over a certain spectrum, then we know that that is going to be called, logically, concave down, or in other words, the graph is opening down. So like we have, I'm going to exaggerate the curve, but basically we have the curvature, the inside of the graph is actually facing downward. These two properties, concave up and down, are globally noted as concavity. Okay, concavity. And this helps us determine, lightnesses of graphs and where the actual graph goes up and curves down, and so forth. So now we're going to be using the second derivative of the function to test for concavity based on its positivity and negativity. Okay, so if you're looking at the theorem here, it says suppose the second derivative exists. Okay, so obviously it has to exist on an interval. Then anywhere that we have a positive second derivative, then we know that the function is concave up on that interval. Wherever we have a negative second derivative, we know the function is concave down on that interval. Okay, and we can bring that even farther and introduce a new term called inflection point. Okay, so I'll come up to that dot in a second, but I want to talk about what an inflection point is. So if you're, look at this graph over here. So if you have a concave upwardly graph, and then it turns into a concave downwardly graph. So essentially the concavity changes sign, then we identify the point in which that happens as an inflection point. The same thing occurs if we start at a downward concavity and then it changes to an upwards. At that point where that occurs, we have what's called an inflection point. So this point is very important in terms of calculus. So the key is just like when we were talking about local extreme points, we're looking for a change in sign. So second derivative changes sign. If it doesn't, then no inflection point exists at that value. So this is going to be, an important part of what we do in terms of the next section. Just remember though, excuse me, just remember that we're also, again, looking for wherever the second derivative is going to be equal to 0 or does not exist. But in most scenarios, we're going to be sticking to when the second derivative is equal to 0 in order to find where this concavity exists. Now, why do we need to do that? Because it's the same thing as previously. When we found critical points, we had to analyze the positivity and negativity around them. So now we have to set the second derivative equal to 0 and analyze the positive and negativity around them in order to determine concavity and whether it's an inflection point or not. That is going to be the key value. That is summarized here for you. But I do want to mention one thing. It says, though it is common for students to do so, we do not treat inflection points the same way we do critical points. When we set the first derivative equal to 0, the resulting values are always critical points. We will once again be setting the second derivative equal to 0 in our process, but the result values of x are only possible inflection points. Possible. So this is a designation that is different, but it's important that you get that whole concept. And one of the things is we're now going to do example problems, as we always do when we go through this. Actually, I got to stop somewhere first with this, but we're going to do example problems. The key is you're going to have to keep the process of first derivative and second derivative separate because they are different, but some of the concepts are similar, some aren't, but we'll go through that in a second. So just to prove to you the whole concept of changing sign right here, that's a highlighter, the changing sign thing here. So just look at this first graph. So this goes from concave down to up. So clearly this point right here is going to be an inflection point because it changes sign. But if we go from concave up to up, so up and then up again, in terms of the concavity, this is not going to be an inflection point. And you can see it from the graph, the concavity doesn't change in terms of what we're doing. So it's important that you see that and note that it's there. So same thing here, the second derivative, so let's say at this point here. So this is an example of a vertical tangent. Okay, so the second derivative fails to exist here, but it is an inflection point. So it's a very fine line. It can be very little confusing here, but basically it is an inflection point because the concavity changes sign. But if you go over here, this is an example of a cusp. So at this value here, again, the second derivative is not going to exist, but because we're going from down to down, it's not an inflection point. So you have to take a look at this as a whole and see that one doesn't always necessarily lead to the other. So you always have to check concavity. You always have to make sure you're finding where the second derivative exists and does not exist. Okay, so instead of rewriting the whole book here, basically for number 3, what I did was I returned to number 1 where we had this function and we took the derivative to get this, if you remember all the 12s. So now we're going to take that even further. So this is what we would do if I gave you a gigantic problem to do this with. Now you would take it a step further and determine all inflection points after determining whether it's concave up or down. Okay, so basically you're restarting this whole process again. You're going to do this time second derivative. So now the second derivative of this is going to be 36x squared minus 24x minus 12. Okay, kind of made a crazy 2 here. 36x squared minus 24x minus 12. And as usual, what do we need to do? We have to set this equal to 0. And solve. That looks like, wow, how did I end up with a double 4 there? That was creative. 184. Okay, so we have to GCF is 12. So we're going to get 3x squared minus 2x minus 1. And we can factor this guy. And when we factor, we're going to get 3x plus 1 times x minus 1, which is going to give us x equals negative 1/3, and x is 1 when we set them both equal to 0. So all old stuff. Now, the key is I'm going to identify this real quick. So these are possible inflection points. Possible, they are not critical points. That is only for first derivative. And they aren't necessarily inflection points. They're only possible inflection points. Okay, so just like before, we are going to do the same number line, except this is going to be a second derivative number line. Just real quick, this is a polynomial again, so we do not have to worry about where the second derivative does not exist. We only care about when it's equal to 0. So that means that these 2 points, values of possible inflection points, are going to be the only values that go on your second derivative number line. So you do the same exact thing. We need to know the behavior in and around our possible inflection points to identify concavity and to identify whether it actually is an inflection point. So what do? We take a number to the left of negative 1/3, let's say negative 1, and we plug it into the second derivative. We take a number in here. We always pick 0 if we can. We take a number here. 2 is right to the right of this. So we are now doing the same exact thing, except now we're going to substitute into this for our values that we go through. So let's pick a color here. So what if we put -1 into this right here? We would get positive for 12. -1 times 3 plus 1 is a negative. -1 minus 1 is a negative. So a positive times a negative is a positive. All right, that is our first one. What if we took 0? Positive 12. We would have 0 times 3 plus 1, which is positive. 0 minus 1, which is negative. So a positive times a negative is a negative. And then for the last one, if we plug in 2, it looks like it's going to be positive, positive, positive. So that happens a lot, by the way. That could, not always, but most of the time, that creates a positive. So right now, we can identify all our concavity. So this is going to be concave down on, well, anywhere there's a negative sign. So -1/3 to 1. It's going to be concave up wherever there's a positive sign. So -infinity to -1/3, union 1 to infinity. So we have our concavity on our graph, which I will show to you in a second. So the only thing left to do is determine if there's inflection points. So what do? We have to look at our graph and say, is there a sign change? So this time we don't need to do these things or anything, right? That's not important. All we care about if there's a sign change. Is there a sign change here? Yes. Is there a sign change here? Yes. Which means you're done. We know that there are inflection points at x equals -1/3 and 1. So again, if they ask for the coordinate, you must plug -1/3 and 1 respectively into the original equation to get your coordinates. I'll do it here in case you end up having to do this on a lab or something like that. I just want to make sure that you get them. Those would be the inflection points that we deal with. But that is the process for this entire thing. Okay, so let's look over the graph. Are you ready? So we identified possible inflection points at -1/3, which is about right here, and at 1, which is about right here. So note, even though the numbers are this is where, by the way, the second derivative crosses the axis. That's what that parabola is, by the way. We have to go to the graph. So let's look. It says that we are concave down from -1/3 to 1. Well, that sure looks like the curvature is facing down. It says that we are concave up from -infinity to -1/3. Well, that appears right. It looks like the curvature is facing up for that entire realm. Also from 1 to infinity. So, same thing. It looks like this curvature is up, facing up for that entire spectrum. So everything looks good so far. And are these inflection points? Does it change? Yes, it goes from positive to negative concavity, and then from negative to positive. So those are inflection points. Okay, so let's move on. I'm going to do another example of that in a second, which is actually going to include the entire process of this section. But I want to stop over in one area real quick, which is understanding what's happening with all of these concepts. It says, so do you think you fully understand what first and second derivatives imply about a function? Well, let's find out. Given the positivity and negativity of the first and second derivatives, choose which graph on the right would best describe the resulting graph. Okay. So, do you understand? Maybe, maybe not, but this is going to tell you for sure. So for letter A, it's stating that one of these graphs has a derivative, which is positive, and a second derivative, which is also positive. So the question is, which graph is it? So this is a sort of a bold question to ask right now because it does really require full understanding of the material. So let's first talk about what this means right here. If the first derivative is positive, what does that mean about the function on that interval? It is increasing. Okay, so hopefully some light bulbs just went off there. So if you look at the graphs over on the right, then doesn't that eliminate two of the graphs? So that should eliminate these two, right? Goodbye. So the only options are 1 or 3 because our function is increasing because it has a slope of a tangent line that is positive. Now, what about the second derivative? So according to this, the second derivative is positive. What does that tell you? You remember this? What does that tell you? It tells you that it's concave up. Concave up. So out of these two, which one has a curvature that is facing up? Well, hopefully, you immediately look at this and go, clearly that is Roman numeral 1. So for this one, the answer is Roman numeral 1 because we have an increasing function that has a curvature that is facing up. So this is a pretty important thing that we're doing right here. Being able to look at this and go, immediately know what's going on with the graph shows full understanding of what we need to do. So let's try B. Most students get B right away because they now understand the concept. So if the first derivative is negative, that means we have a decreasing function. If the second derivative is negative, that means we have a concave down function on whatever interval. So of the two that are decreasing, which are 2 and 4, which one has a curvature facing down? Well, clearly that is Roman numeral 4 right here. So this is a pretty neat concept. I like doing this before I do the big finale problem, just because it really shows you that these two things are completely different concepts, but luckily they're done in very similar ways, which makes the process not so bad in the long run. So what we're going to do now is we're going to go through with the function f of x equals x cubed minus 3x squared, and we're going to do a complete analysis of this by finding when it's increasing and decreasing, all local extreme, where it's concave up and down, and all inflection points. All right, I gave you lots of space because, oh boy, you're going to need it. So here we go. So what's the first step? So all the way in the beginning of this section, we had to determine when we were increasing and decreasing and local extreme points. That was our first process. How did we do that? By setting the first derivative equal to 0. So the derivative of this problem is 3x squared minus 6x. And if we set that equal to 0, we get a typical binomial, which normally requires some type of GCF. GCF is 3x, so we get x minus 2. And if we set both of these equal to 0, then we're going to get x equals 0 and x equals 2. Just as an aside right now, you'll see I'm going through the algebra fast. Why? Because you've taken a ton of algebra and you should know it inside and out. That's not to make you feel bad if you don't. That's just telling you that if you don't understand the algebra, you need to look on your own and figure it out. You have to look up and do practice and things because it's hard to do calculus if you can't do the algebra to get there. That's the best way to put it. Okay, so what are these? These are essentially my critical points or values, doesn't matter. Okay, CPs. So, what did we do with these critical values? Well, first of all, we have a polynomial, so we don't have to worry about where the derivative doesn't exist. So therefore, we make a number line, right? We put our critical values on the number line, and then we do testing derivative values to the left. Looks like -1 would be here, 1 would be good here, and 3 would be here. So never choose the critical points themselves. Students make a mistake and do that. You're just going to get 0. So don't do so. All right, so what are we doing? We're going back to this equation right here, and we're testing for positivity and negativity. So if we plug in -1 into here, we're going to get a negative, and if we plug -1 into here, we're going to get a negative. So a negative times a negative is a positive. If we plug 1 into here, to 3 times 1 is 3. 1 minus 2 is a negative, so we're going to get a positive times a negative, which is a negative. And then 3 creates a positive for both of them, so we're going to get a positive. So this is our tree that we need. This is our number line, first derivative number line. And this is what's going to help us decipher all the important information at the bottom here. So what do we get? Well, we start with, let's do decreasing. So we are decreasing anywhere you see a negative. So on 0 to 2. We are increasing anywhere you see a positive. So we're increasing on -infinity to 0, union 2 to infinity. Okay, so these are our values. No, there's no more graph over here to verify all this stuff. It's literally exactly what the graph would look like if you went through with it. Okay, so what's next? We have to determine local extreme values from this graph as well. So do we have sign changes for both of these? It turns out we do. They're both sign changes. So we have to determine what type of extreme locals that are created. Well, this goes from, are you ready? It goes from positive, positive, positive to negative, negative, negative. So what do we create? We create a local max at x equals 0. And this one goes negative, 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 the positive, positive, positive. So we create a local min at x equals 2. Okay, just as a side note, as I've always been doing, the coordinates for this are 0, 0, and 2, -4 that you get by plugging 0 and 2 into our original function. Okay, so this is the first half of the answers. This is the important values that tell us where this graph increases and decreases and local extrema. So then what about the second half of the problem? Well, that's what we just did here. We need to determine concavity, and we have to determine inflection points. So here we go. We take the second derivative of this function. So look at this one and take the derivative and get 6x minus 6. We set that equal to 0 and get x is equal to 1. Okay, so this, in this scenario, is not a critical point. It's a possible inflection point. Okay, possible inflection point. So once we get that value, we can create our second derivative number line. It's the first number line in which we only have one possible inflection point on it, which means then we need to test anything to the left and anything to the right, just like that. All right, so we can actually, we probably don't even need to do a factoring for this. We can just use this. Super easy. If we plug 0 into that equation, we're going to get a negative. If we plug 2 into that equation, we're going to get a positive. So this is our signage for our second derivative number line here. And that's what we're going to use on the bottom here to sort out what we need to know. So where do we start? We are concave down anywhere we're negative. So on -infinity to 1. We are concave up wherever we are positive, which is from 1 to infinity. And do we have a sign change? We do, which means there's an inflection point at x equals 1, and I think that coordinate, I don't have it actually. It's going to be, it looks like 1 minus 3, which is 1 negative 2, I believe. 1 negative 2. Okay? So basically, in the scope of this problem, this would be like a 20-point problem that would include, and by the way, I don't know how it's going to go with the online setting, but in class setting, usually this is like a 17 or 18-point problem to be able to do this whole thing. Okay, just to let you know. So now that we are done with this problem, this is the ultimate problem. So if you want to come back and you want to find out how to do this process, this is it. This problem details the entire procedure. And the whole reason why you learn it is the ability to possibly take this information here and here and build the graph based on that. Because you can, along with some x-intercepts and stuff, and y-intercepts. But that's kind of the idea, is that this information is golden for being able to hash out what a graph looks like. You're tasked with finding all of this important information in the section. Lots and lots of practice needed.